This presentation is an introduction to light, its intensity and its quality. In this lecture, we'll be talking first about what is light, about the physical properties, how light is measured, what light does for plants, how to increase light with lighting sources, and also how to decrease light. So first off, what exactly is light? Visible light is a small part of the electromagnetic radiation spectrum. Plants utilize light from 300 to 800 nanometers, but we can only really see light that is 400 to 700 nanometers in wavelength. When I say nanometers, I'm referring to the length of one wave, which means that the higher the wavelength, the more distance between each wave, and the lower the wavelength, the shorter distance between each wave. That brings us to measuring light. The first thing to know about light is that it behaves as both a particle and a wave. A light particle is called a photon, and a photon's energy is equal to the energy equivalent of one wavelength, meaning that one wavelength can be considered a photon. The energy is also inversely proportional to the wavelength, meaning that the longer the wavelength, the less energy it contains, and the shorter the wavelength, the more energy that it contains. There are a few measures of light to consider when growing plants. The intensity, which means quantity, and the irradiance, which means quality or spectral characteristics. For that reason, a spectral radiometer is used when measuring irradiance. There are a few different ways to measure the intensity of light. First off, a quantum meter gives an instantaneous reading of the moles per meter squared per second. The quantum meter works by measuring how many micromoles of light per meter squared per second are striking the surface, or you can see here what the shorthand is for that. Also to note, 6.022 times 10 to the 23rd photons equals 1 mole, also referred to as an Einstein. Thus, 1 micromole is 6.022 times 10 to the 17 photons. This is a photo of a light meter, and as you can see at the very bottom, it has micromoles per meter squared per second. The daily photosynthetic integral, or DPI for short, is a measure of the total amount of energy from incident light in the period of a day. The amount of energy is calculated by measuring the PAR, or photosynthetically active radiation, in watts per meter squared instead of the number of photons. So next up, what does light do for plants? Light provides the plant with a source of energy via photosynthesis. This allows the plant to grow and develop, and the reaction converts water, CO2, and light into sugars and molecular oxygen, and eventually energy. Listed here is the basic conversion of 6 CO2, 6 water, plus light to yield 1 glucose molecule and 6 molecular oxygen molecules. Light also provides a heating source for the plants. It's an important balance between intensity and duration of light that strikes the plant that will determine the plant's overall temperature. The higher the light, the warmer the plant will be. Light may also signal the plant when to bloom. Photoperiodic plants rely on a critical light or dark period to signal when it is time to enter into a blooming sequence. This happens with plants such as mums and poinsettias. Light may also influence the shape of the plant. This is referred to as photomorphogenesis, which basically means the changing of shape due to light. Also, each leaf will be arranged in such a way to achieve the maximum amount of light interception. This is referred to as phyllotaxy, or the arrangement of the leaves. The quality of light in photomorphogenesis also plays a large role. That brings us to increasing light. When the light from the sun is not enough to sustain and grow a crop, supplemental lighting sources may be used. Types of lighting sources include incandescent, fluorescent, low-pressure sodium, high-pressure sodium, and metal halide lamps. Incandescent bulbs have a low ppf, or photosynthetic photon flux, which means that they have a low spectral output and intensity that does not complement light needed for photosynthesis. They are, however, used in some situations when only a low or small amount of light is needed. Fluorescent bulbs have a better spectrum for photosynthesis, but a low intensity. This means that lamps must be placed right on top of plants to achieve any desirable results. Low-pressure sodium lamps are good for intensity, but have too much yellow light in their spectrum, which is not conducive for photosynthesis. High-pressure sodium have a larger spectrum than low-pressure sodium and are better for photosynthesis. This is an example of a high-pressure sodium bulb. Metal halide, which are very commonly used for flowering ornamental crops, have a much larger spectrum for photosynthesis. However, the spectrum will vary with a different metal content for each type of bulb. These are two photos of metal halide bulbs. Finally, we have LEDs, which are light-emitting diodes. They have a spectrum that can be custom programmed for different crops. However, right now, the intensity of these lights is not very great, but increasing the intensity is in development for the future. Below is a photo of a magenta light that's used on seedlings. Here you can see an example at a trade show of the lights and their ballasts and how it might be displayed or set up in a greenhouse. So that brings us finally to decreasing light. So we have to ask, why do we even want to decrease light? We might want to decrease light because high-intensity light can be damaging to plants. As mentioned earlier, the more light that you have striking a plant, the warmer the plant is likely to be. Decreased light is also used in propagation houses to cut down on cooling costs and water usage. A shade cloth is the easiest way to directly decrease light. The weave of the fabric will determine the amount of light that penetrates. The tighter the weave, the less light, and the more loose the weave, the more light. That allows shade cloths to be available in incremental values. Different colors can block certain parts of the spectrum, such as a blue shade cloth blocking all colors except for blue and transmitting only blue light. It's important to note that green shade cloths transmit green light, which is not good for photosynthesis, as red and blue light are more photosynthetically active. Here's an example of an automated shade cloth system in a greenhouse. That brings us to the end of our presentation. If you have any questions, please direct them to me, Miles Gennard, at gennard.14@osu.edu. Thank you.